So, hi everyone. We'll begin shortly. Let me just log in from my other device. So, today we will be discussing Bayesian auctions, and there are like a few categories of Bayesian auctions, all of which I will discuss one by one. But if you do have any specific questions about Bayesian auctions, please let me know. Sorry, give me a moment. One minute, let me rejoin from here. Yeah, like I was saying, so if you have any specific questions in Bayesian auctions, you can tell me so I can, address those better, basically. Okay, I think the sound is better now. Yes. Okay. So just give me a moment. Let me see if this is set up correctly. Okay. Okay. Okay, great. So let me just share my screen. Okay, let's go to, this is week 6. So also, by the way, we will have a review session in a very short while, actually. And you will be informed of the review session for this course shortly. It should be sometime next week or maybe the week after that. So just look out for that email also. Right, yeah, I think this is correct. Okay, so let me share my screen. So I don't know why there is this lag. It's a problem here. This internet is, I think, a bit not so good. Let me restart that. Okay, it's better now. Okay, so before we dive into auctions, I just wanted to give like a very quick recap of random variables, because we use random variables quite a fair bit in the sorry, what the hell is this? Yeah, because we use random variables quite a bit in auctions, and I'm going to talk mostly only about the uniform continuous random variable. But just I've defined the probability density function, but it's just a bit of a it's a very simple form of continuous random variable. The uniform random variable is actually I think the simplest random variable you can find, and I guess that is the reason why we use that a lot in some of this auction theory. But my point was that if you understand the method we are using, even with the uniform random variable, if you understand the method, if the function of the random variable changes, for example, instead of uniform it becomes normal, or it becomes binomial, it becomes something else, like the logic will still remain the same. This is in case if you want to sort of study it further or something. Okay, so basically a uniform random variable in the most general sense on an interval a comma b is the simplest one. Like, if we in the discrete version, if we say something like, you ask somebody a question, something like, pick any number between 1 and 100, say, suppose, right? Or 0 and 100. So if you take the uniform continuous version of that experiment or that trial, that is your continuous uniform random variable. Okay, so I'm just trying to give you an intuition of what it really means. So if you want to read more about random variables, I would recommend the book. It's called, I think, Mathematical Analysis and Mathematical Statistics and Data Analysis by John Rice. I've given the name of the book in the references in this slide, so you can check it out. I think the book gives a very clear and very concise explanation of random variables. I mean, on probability in general, but our concern is mostly with random variables. So I'm talking about that. So basically, in a uniform random variable x on an interval a to b, it has the very simple, very convenient property that if you take any subinterval of length x, say, suppose, on that, this is the, like, say, suppose the whole interval a comma b, in that if you take some length x, then the probability density function is given as 1 upon b minus a, and hence the probability that the random variable x lies within that tiny interval x is equal to x upon a minus b. So what do we mean by probability density? So the way I understand probability density is that, like how you, I don't know if you guys studied this in physics, but, like if you consider the density in terms of mass, right? And if you're looking at a line object, a linear object, so then in that case, the length into the density gives you the mass of, of that linear object. Like if it's a stick, say suppose, right? If it's a stick and it's a uniform homogeneous stick, and if you take the length x of that stick and you know the density, then the density into the length gives you the mass of the stick. So probability density function works in a similar way. Of course, we're not calculating mass, we're calculating the probability, right? But what we are saying is that the probability density is given by the entire interval length, which is b minus a. You can just take 1 upon b minus a as the density because it is uniform, right? That entire b minus a is uniformly distributed over that interval a comma b. So the density becomes 1 upon b minus a. And if you need to calculate the probability that the random variable is lying in that tiny interval x, or it may not be a tiny, actually x can be any length x. So if any subinterval x accommodates the random variable capital X, so as a side note, generally in probability theory, we denote a random variable as capital X, and it's some realization as x, like small x, or capital X, something else, with some what do you call it, subscript, right? So x or capital X, capital Xi are all named as random variables, and a realization of it is generally written as x. So, but here we are using a slightly different notation in our auction theory. So please don't get confused by that. We are just trying to reconcile two different branches of mathematics here. So there's going to be a little bit of clashes. So here, what we are saying is that here I'm taking length small x, but you can take it as h, you can take it as d, you can take it as anything. Here, small x doesn't mean a realization. It just means that there is an interval of length h, let's say, instead of x. So then in that case, the probability density is this, and this is what it means, that if that length h is lying within that interval a and b, then this is the probability density function. Otherwise, it is 0. So that was the probability density function. The other important function which you should be familiar with is the cumulative density function, which is the CDF. And this is generally denoted as capital Fx. Okay, the small f denotes the probability density. Capital Fx denotes the cumulative density. And capital Fx is defined as the probability that capital X, the random variable X, is any value less than or equal to X, where X is now some length, some interval, between that in its domain, like between 0 and 1 or a and b, whichever you have, whatever you have defined the interval as. So here I've just given the simpler version for the uniform random variable over the interval 0 comma 1. Then the cumulative density at 0 is of course 0, because x less than equal to 0, we know it, the probability is 0. So the cumulative density function will also be 0. When x is lying between 0 and 1, any length x between 0 and 1, the value of CDF is x. And if x is greater than 1, it is just 1, right? Beyond x, the whole because we're taking the cumulative density function. Cumulative probability, meaning the entire probability up till that length. So if the entire interval is covered, then that means what? We have taken the entire integral or the summation of all the possible outcomes, probability of all the possible outcomes within that interval. That is going to be 1, right? So don't get confused. This is the difference between CDF and PDF. But this CDF is kind of useful because many times you will find we are in a situation where we have an expression in such format, probability that capital X or V or B or something is less than something, right? I've used the notation capital X and small x here, but in your mathematical calculations it may be something else. Okay, but the expression will be of this form: probability that some random variable is less than or equal to some other value is nothing but the CDF. Okay, and the CDF is what? The value of the CDF is given as below. And to make matters simple, I've taken this as the uniform variable over the interval 0 comma 1. So if you want to know the probability of capital X less than or equal to small x, when x is lying in that interval 0 comma 1, then that is simply equal to x. And this is not something particularly complicated, because if you just, CDF is nothing but if you take the integral up till that value x, then this is what you get, right? It's just the integral of the PDF dx. So PDF is nothing but 1 in our case, in the 0 comma 1 uniform variable. So it is nothing but integral of dx from 0 to x. So you get x. So just to save us the struggle of doing that integral, instead of doing that integral to calculate the probability, you can just directly use the CDF. And I think it is used in some places in the lectures also. I don't remember exactly, but I remember seeing it somewhere. But even if it isn't, this is like, the standard thing. So I just thought it a good idea to give this recap. So I will go over this question, although this is very kind of similar to what you have in the lectures, but this is a little bit more of a general, more generalized version of that example which is there in the class. So I thought this would be good example, because whatever rationale or the logic we use to solve this particular example, you can use even if the function of the the bids or the strategies is something else. So either the problem is that your actually this week's assignments cover a wide variety of all the questions in this particular topic. So it's very difficult to find a question of the same level of difficulty as your syllabus, which is not already in the assignments. So, and the rest, most of it is already there in the lectures. So I'm just picking something which might help you understand the calculations maybe a little bit better, or the rationale or the method maybe a bit better. And this is the general method you will use for these type of questions. Okay, so let me just open it here also, just give me a moment. Okay, I'm just reading out the question and then I'll write it alongside. There are two players who want to own a prized object up for auction. So the valuation of each player I is VI, and V1 and V2 are independently and uniformly distributed on 0, 1. So let's write that down. Oh, sorry. Okay, so there are two players and we have V1, V2 as the valuation, which is distributed over this interval. This is uniform, this is U. Okay. The value Vi is known to player I, which is what we normally do, that I know my own valuation. Okay. Each player bids Bi, which is a real number. So the bidder with the highest bid wins the object and pays the bid. So sometimes in the question it will just be written that it's a first price sealed bid auction. So then you already know some of the basic conditions or the rules of the game. And some other times the rules may be explained in this way. So please read it properly. If the rules are not if it's not mentioned straight off that it's first price, blah blah blah, and if the rules are given, then read the question properly, because sometimes there may be some variation in the question. Okay, so the loser gets zero payoff, and what you need to do is you need to find a symmetric linear Bayesian Nash equilibrium where Bi is equal to A plus CVI for some constants A and C, and you have to determine the constants A and C. Okay, so let me go back to, I'm gonna find my window, 1 minute. Okay, so this is the setup. So let me just recap what we need to do over here. First thing we need to do is we need to write the utility function of any one player. So, just for the sake of simplicity, you can take Bi, Bj, write it in general terms, or you can write it as 1, 2, whichever thing you prefer. Okay. Now, what we are given, say, suppose I write it in terms of I and j, what we are given, isn't it working? Oops. Yeah. What we are given is what was given, Bj, right? Yeah, Bj is equal to A plus C or C plus A. Cvj plus A. Okay, this is given to us. What we need to prove is that, sort of to prove, is that Bi, sorry, not Bj, Bi is also of the same form, Cvi plus A, and determine A comma C. So this is like a more general question of whatever we've discussed in the lectures. You're given that the other player, your opponent, has a linear strategy, okay? This is Cvj plus A of this form. And you have to prove that if the other player's best response or their strategy is this, then your best response is also going to be linear in the same form. And while you're at it, you have to also determine the values of A and C. Okay, so we can start off simply by just first writing nothing very complicated, just write the utility of player I. This we know, we've studied auctions before. This is not something new. This is first price sealed bid auction. So utility of player I, when their strategy is Bi and the other guy's strategy is Bj, is what? So this is first price auction, right? So my valuation is Vi, right? And if I bid Bi and if I win the bid, if Bi is greater than Bj, Okay, let me write this more neatly. So my valuation minus my bid, right? Because this is first price sealed bid auction. If, on the other hand, if BI is less than BJ, then I get nothing and I pay nothing. So this is the standard first price sealed bid auction. Now, in this, it's just let's take one step back to just remember what are the things we know here and what are the things we don't know. Okay, what all we know, what all we don't know. So in this, my own valuation, I know my valuation, right? Because that is, first of all, the setup of the game. And also we are assuming that there is no uncertainty in my own assessment of my valuation. Like if I have to buy, say, a painting or a house or whatever, which is up for auction, I already know what its value is to me. So VI is a number, okay? It's not a variable for me when I'm talking about my value, my utility. BI is also known to me because I'm choosing it. I'm the one who's choosing BI over here. So BI is a real number, okay? BI is a real number which I'm choosing, and hence BI is also known to me. What is not known to me is this value of BJ. Okay, what we have written over here, BJ is unknown to player I, right? We don't know BJ. All he knows, all player I knows is that BJ is of the for CVI plus A, right? Sorry, CVJ plus A. And in this expression, VJ is also not known, is unknown, right? But we do know, but we know that Vj follows a uniform distribution over the interval 0, 1. Okay, so this is what we know and what we don't know. Okay, I've just like spelled it out in this format so that we understand what, because sometimes it's very easy to get confused between VI and VJ and all that. So let's be clear about what is known and what is not known. So now let's move to what is the expected payoff. So this is a utility function. Okay, this is given by these conditions and these values. Now, if I have to write the expected payoff of player I, say suppose this is expected payoff, then it will be what, and the what value what is the payoff when you win, which is VI minus BI into probability of win plus what you get when you lose into probability of not win or lose. Is like nothing new. Now VI minus BI into probability of win is nothing but the probability that, or let me use small brackets only, BI is greater than BJ. This is the condition for winning, right? So now probability of BI minus BJ, let's see what we can do with this expression. This expression, we are going to just redo this in a slightly different way. So BI is greater than BJ implies that BI is greater than this expression we know, A plus C VJ, right? This further implies we just rearrange the terms. VJ is less than BI minus A divided by C, right? So this probability BI greater than VJ is nothing but this probability that VJ is less than BI minus A by C. So therefore expected payoff of I is equal to VI minus BI into the probability that Vj is less than Bi minus A by C. So now we are seeing a familiar expression here. Now let's remember that vi over here is a random variable, like, uniform random variable over 0 comma 1, right? So if you want to know the probability that a random variable, uniform random variable, is less than a certain value, then we just discussed that in the, in the recap I was giving. That is nothing but what? What did we discuss? Anybody wants to answer? It's okay, you can just attempt. There's no problem with that.
Probability density function.
No, it's a CDF. So that's why I discussed it. Let me go back to the slides. Okay. So see that's what I wanted to actually correct, because this is the part which sometimes if you have not studied probability too much, then you may forget. So this is the probability density function. And this is the probability and the cumulative density function, which is the CDF. This CDF is capital Fx, which is defined as the probability that a certain random variable is the probability of a certain random variable taking a value less than or equal to x. Now, in a continuous random variable, the equality actually does not matter, because the probability of any particular point is actually almost zero. Not almost zero, it's actually precisely zero. It is exactly zero. So whether you write it as x, capital X less than small x, or capital X less than or equal to small x, it doesn't matter. It's the same thing. So this is what a CDF is. So what we have written over here, this is nothing but the CDF, right? This expression, probability Vj less than Bi minus A by C, is the CDF. So the value of this thing is going to be nothing but the thing itself, because it's the uniform function. Right? Let me write this separately. Is this making sense? I don't want to make it too messy, but I just wanted to expand this expression a bit. So is this clear?
Yes, ma'am, but I have a little doubt.
Yeah.
In the lectures, we always considered that a function exists between 0 to 1. So the probability its value is less than 0, it is all minus infinity to 0, it is always 0, and 1 to infinity, it is always assumed to be 0. So the function exists always between 0.
No, the probability is 0, but the CDF is not 0. CDF is a cumulative probability.
Okay.
So, okay, I am drawing this here just to explain it. Say, suppose this is the interval, this is 0, this is 1, and this is some function. I'm not drawing a uniform function right now. Okay. Now, in this, if what you want to know is that there's some random variable x, and you want to know the probability that it falls within this interval. Okay. Then this is given as equal to fx into x. Okay, fx is some probability density function. Okay, is that making sense? Now, similarly, you will do this for all of it, but what we are looking at is the CDF. Okay, CDF is a different beast. CDF means that what is the probability that x is less than or equal to small x, which means we want to know this entire probability up till this point, x. Okay, so if you're taking the cumulative probability, then after this point, this whole thing has become 1, right? If you take the integral up till 1, the total probability is 1, because we know for sure that after this point, we know that within 0 and 1, capital X, the random variable is definitely going to be within the interval 0 to 1, right?
Right.
So that is why the CDF becomes 1. Probability of X being outside of X is 0. Outside of 0, 1 is 0. Okay?
Okay.
Yeah, this is the CDF. And yeah. So this is why I was trying to explain that this expression here, probability Vj less than or equal to or just less than Bi minus A by C, this is the CDF. And if this is confusing, what you can do is you don't need to, you don't need to actually use the CDF. It's just a thing you will find actually many books, they use it like that. So I thought I'll explain it. Otherwise, if you want to take the long form, you can also do it like this. There's nothing wrong if you're not too worried or too encumbered by using integrals, then you can just take this vi bi outside because these are known values, they're not variables. So we want to know the value of this integral actually, dvj. This is what
Right.
it's
This is what
equivalent
I used
is.
in the lectures.
Sorry?
This method was used in the lectures.
Yes, I'm just giving you a shortcut, that's all. I'm not teaching you something different. I'm just giving you a shortcut because I understand it. I find it easier to do it this way. But if your intuition is better tuned to this, then this also is going to come out to this. You're evaluating Vj here between this interval. And this is your into bi minus a by c. You get the same thing. Because this expression CDF is the integral of the PDF. That's why it's simplified to that.
So this new method, I mean, the method that you have just shown is based on PDF, and the one that you were using previously was based on CDF.
Yes. So you need to just understand that CDF is the integral of the PDF.
Right.
So if you are using integral, and it's a very simple, it's a uniform random variable.
We don't have to perform the integral then.
Yes, you just save yourself a little bit of time, that's all. If it's a complicated random variable and you don't know what the CDF is, then it doesn't make sense. You are better off using the integral.
It's always
But if it's
to learn something new. So can you continue with the CDF version?
Okay, yeah, sure. So, like I was saying, like in this particular case, in the uniform random variable, that too over the interval 0, 1, the CDF is very simply just the value x, small x. So that is why it becomes very simple. It's just a one-step shortcut, that's all. So this is what we came back to. Or let me just write this alternatively. Okay. Let's come back to this expression. This is the final expression we got. Now our job is to maximize the expected revenue for the player I. That's what we want to do, right? Now for player I, if I am player I, everything else is varying except for BI. Right? I'm choosing BI. BI is my strategy, right? VI is just a number. I know it. I can't like exactly change VI. It's a real number. A and C are constants, and we have eliminated all the BJ, VJ variables, right? So now the main thing which I can choose to maximize my payoff or my expected payoff is with respect to BI. So we will take a partial derivative of this with respect to BI, and let me rewrite this to make the differential easy. This is plus ABI minus BI square and minus ABI. Okay, so let's differentiate this. You get 1 by C and VI plus A minus 2BI equal to 0, right? So from here you get BI is equal to, this is 1 by C is also there. Yeah. A plus VI by 2, or actually C you can just delete, it doesn't matter, by 2. Right, so this is the form we are finally getting for BI. Now we know we know, or we need to prove, let's say, no, we don't know, we need to prove that BI is of the form, what was given? A plus CVI. Right now, we can see a very similar expression taking shape over here. BI is equal to VI by 2 plus A by 2, right? So now in this, if we put C is equal to half, we get the VI by 2 equal to CVI part. And if we put A equal to A by 2 equal to 0, then A disappears and we get BI is equal to VI by 2. And we can say, since we have solved for A and C, you can say Bj is also equal to Vj by 2. So the proof is, this is how you do the proof. Okay, so this is like a more general proof of what we had taken in the class, but you can get it in any other form also. So you can get the strategy as something else for one player, and you may be asked to prove that this is something else, is like some other symmetric equilibrium or something like that. So this is one of the equilibria, and the reason why this is the most discussed one is because it's a symmetric equilibrium. All the other equilibria tend to not be always symmetric, but this one comes out to be one of the very nice Nash equilibria in this particular set of auctions. So this is the first price sealed bid auction with the linear strategy, and we have taken the uniform random variable as 0, 1, and this is the proof. So any other question in this? If not, I will move on to the next question.
Ma'am, just a small question.
Yeah.
In the lectures of this week, I mean week 6, we have the professors have shown the proofs that the Nash equilibria for an auction, first price sealed bid auction, let it be V by 2 and V by half of V and half of V1 and half of V2, right? And they just want us, and they show the proof that it is the Nash equilibria. We have to prove that it is the Nash equilibria. But we never derived this is the Nash equilibria.
Yes.
We have derived the Nash equilibria. We just have proved that this is a Nash equilibria. So is it, I mean, so there are other Nash equilibria are also possible?
Yes. So see, the thing is that this is a continuous random variable. Okay, and that means that let's understand what we mean by a continuous random variable. Sorry, there's some sound coming from the lab, I think. So what happens is that, if you go back to your normal Bayesian game, which we discussed, say, last week or the week before that, in a normal Bayesian game, what you have is, say, suppose there are two players, and the player 2 has two types, right? Like example, Battle of Sexes or Kuno duopoly or Bertrand duopoly. The player 2 has two types. One is high cost, the other is low cost, or one, is interested girl, the uninterested girl. So we were just taking two types. So it was simple, we could just we did a similar calculation. If there is uncertainty in any element of the game, you need to take the probability of all outcomes and the payoff from all outcomes, right? So that is the standard way in which you operate. Now, in this particular case, what we have is that the other player, if I take just the two-player example, I'm the one bidder, player 1, the other bidder is player 2, and the bidder 2 can be of infinite types, because his valuation is varying over a continuous interval of 0, 1. It means there are infinite possibilities of his type, right? So, and I don't know which one I'm going to be playing against, right? If I'm bidding in an auction and that person is completely unknown to me, some unknown person is bidding in that auction, all I know is that his valuation is going to lie in some interval, which we have normalized to say 0, 1, that it's not going to be less than some value and it's not going to be more than some value. That is all I know. But I don't know within that entire range what it's going to be. That means I'm playing against players of infinite types. And that is why this sort of a game can have infinite number of strategies of the players, and hence it can have any number of Nash equilibria. So we cannot sit and compute all the Nash equilibria like we do in the discrete example. But what we can do is we can find some of the Nash equilibria which are very symmetric, or which are very easily mathematically solvable, or which are very intuitive. Like in this case, the basic conclusion of a first price sealed bid auction is that it is never a good strategy to bid your own valuation in the auction, right? Because even if you win the bid, you're not going to want to bid your valuation, because then you get zero payoff, right? So you will always want to bid something less than your own valuation. That is the first thing. The second thing is that if you're bidding, so on the one hand, increasing your bid amount is increasing your chances of a win. But at the same time, when you're increasing your bid amount, you're also decreasing your revenue, because you have to pay that bid amount also. So that is why, if you see in the end, the function we get is a quadratic function in BI. And that is how it is kind of characterized mathematically, that when you increase, on the one hand you want to increase the BI, on the other hand you want to decrease it. So there must be some value at which the whole game is optimized for you. And that value is what we have calculated as VI by 2. So at VI by 2, the strategy is most optimal for you. And that is one of your best responses given the other person's strategy, right? So in this case, we are taking the strategy as a function, right? We're not taking strategies of the other player as a number. We're taking the strategies as a function. So if this function is linear, then this is what comes out to be the best response, or what the symmetric equilibrium is. Now, if the other player is choosing their strategy as per some other function, then again you will do this kind of a similar calculation, and you will find out what your best response should be. So when you are doing this thing in a symmetric game, for example, like in this case, both the players are identical in every aspect, right? We have not made any kind of a difference between them. So in this, for example, there are two players. That's why I did it as I and J, because when you say I and J, I could be player 1 or I could be player 2. So it's a general outcome, which means that if the other player is taking one strategy, and for player J, for example, and BI comes out to be this, then you can generalize it to both. It holds true for both of them. So if you are given some other strategy, like, V2 square by 5 or something like that, or V2 square by V2 square by K or something like that, then you will, again, if you take it as I and J and calculate your own best response, and I'm just making this up, I have not calculated it. But if it comes out to be symmetric, then that means that is another Bayesian symmetric Nash equilibrium. But like I said, because infinite types exist for both the players, hence there can be any number of strategies. The strategy of the other player can be any kind of a function, right? And it's a continuous function, so it can take any real number as a realization. So it will definitely have any number of Bayesian Nash equilibria. So this is how this week's content is actually very different from previous weeks, and it's a little bit abstract in that sense, which is why I wanted to take over it a little bit slowly. So while we are talking about it, I thought it would be a good idea to also discuss the expected revenue to the auctioneer. I'll take it only for the first price sealed bid auction. The rest, I think, is very similar reasoning for the second price also. So you can go over that. It's already there in the lectures, but I thought I'll just recap it here. Okay, so what we want to know is the expected revenue to the auctioneer, not to the players. What is he going to make, right? So I've written ER as short. So expected revenue is going to be the maximum of the two bids, right? Maximum of B1, comma B2, whichever is bigger. And from the previous result, we just found out that this is nothing but maximum of V1, comma V1 by 2, comma V2 by 2, because B1 and B2 came out to be V1 by 2 and V2 by 2, or half of maximum of V1, comma V2. Okay, this is not complicated. This is pretty straightforward. Whatever, it's the same thing which we have been doing till now. Now, what we are trying to do here in the next step is we'll try to generalize this result for both the scenarios where V1 is greater than V2 or V2 is greater than V1. So say suppose you have an interval like this. Okay, this is 0, this is 1, and this is some V, and this tiny interval is dV. Okay, so now why we are taking V and dV, you will understand in a short while. So what we are saying is that we're trying to take it one step at a time. Okay, what we are trying to say is what happens if V1 is sort of, just more than V2. Okay, it's not, I'm not saying it's infinitely more than V2, but it's just a little bit more than V2. So this you can write if V1 is greater than V2, but it is only a little bit greater, right? So you can say that V1 is lying somewhere between 0 and V. And when I'm saying, sorry, V2 is lying somewhere between 0 and V, and V1 is only a little bit more, means it is lying somewhere between V and V plus dV. So, or let me write it more mathematically. This implies that V1, let me write V2 first. V2 belongs to the interval 0 to V, right? And V1 belongs to the interval V comma V plus dV. So we are saying that V2 is somewhere here in this space, and V1 is somewhere in this corner. Okay, so this is what we're considering as the limiting case. So then in that case, the expected revenue is going to be what? Probability of each event, right? And then we will come to the, let me write both actually first. Probability of V1 greater than V2 into half of max V1 comma V2 plus probability of V2 greater than V1 into half max V1 comma V2. So actually this should have been before, but anyway. So this is first of all what the expected revenue to the auctioneer is going to be. Probability that V1 is greater than V2 into the whatever the value it is, and the probability that V2 is greater than V1 into the value which is half max V1 V2. Now probability of V1 greater than V2 we just explained over here. This is the whole thing. So let's take the first case. is equal to, let's split it up into both the conditions. So when we are saying this, so look at the highlighted part. When we are saying that if V1 is greater than V2, then that means V2 belongs to 0 comma V and V1 belongs to V comma V plus dV. Then what we're looking at is the probability of both these events occurring simultaneously, right? So we're looking at the joint probability. That means we are taking the probability of V2 belonging to 0 comma V into the probability of V1 belonging to V comma V plus dV. Right? This is what we are trying to say over here. So probability of V2 belonging to 0 comma V is what we just agreed in the in the previous very lengthy discussion. This is just V, right? Probability of V2 belonging to 0 comma V, you can write it if you want to write it in the same way, you can write that this is probability of V2 less than or equal to V. The same thing, right? So this value becomes V, and similarly, by the same logic, this value becomes dV. So this is V dV. This is the thing is V dV. Now, if you do the similar reasoning, but you invert it, V2 is greater than V1, then you will write the same thing, but you will write it ulta, right? Now they have swapped places, that's all. There's nothing else that is different. The same thing, so you will obviously get the same value, right? This. So now we know the probability of both these things happening. Let's go back to this expression. What is the expected revenue? This is the expected revenue. Probability of V1 greater than V2 into half max blah 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 plus probability V2 greater than V1 plus half max blah blah blah. Right? Let me name this as equation 1. This is 2. This is 3. From equations 1, 2, 3, we can now say V comma dV into half max plus V dV into half max V1 comma V2. Okay, so this is, I hope this is so far so clear. And this is the limiting case we were taking when V1 is just greater than V2 or V2 is just greater than V1, right? So then in this case, we can just simplify this. We have written like a whole lot of things here. Instead of V1, V2, we can just simply reduce this to say 2V dV into half max. Oh, sorry. This 2 cancels out, right? So what do we get? Did I miss something? No, we got the same value. So, no, 1 minute, I missed something. Yeah, so this thing is V, right? I forgot to substitute that. So this 2 cancels out. This is V dV. Now max V1, V2, we can just take as V because we are taking a general term here. We are taking whether it is V1 or V2, we are just taking both the values as a variable V over here because we're using both of these as variables. So you get V square dV. Now this is what we have taken so far to be as the expected revenue for that infinitesimal increase, but the total expected revenue over is, I'm writing the same thing. It looks a bit weird, but let's use some other expression, otherwise it looks confusing. Integral over 0 to 1 v square dv. So you get v cube by 3, 0 to 1, it comes out to be 1 by 3. So this is the, the simplified thing of what the expected revenue to the auctioneer is going to be. Now, again, I have not taken the case where the strategies are something else, because in that case, the question becomes kind of different. Okay, so I've not considered that case, and also you already have the only other simpler question that can be made from that. You already have it in your assignment, so I don't want to take that. But if you need to calculate the expected revenue, if the strategies are something else, then the only thing that will differ will be this value max of V1, half max V1, V2. Right? This is the value we got for the strategies that were linear. Now, if the strategies are not linear, you will do this previous calculation, whatever we did here, and you will derive the final, expressions for that, and you will use that as the payoff. The probability part will remain the same. That's the main thing. I don't know at what zoom level this is visible properly, but this part which we did, the initial part, this was for the linear strategy. So this calculation you will do for, say, whatever, quadratic or any other type of strategy function, and you will derive the final value, whatever bi, here we got is vi by 2, bj is vj by 2. So whatever expression this comes out to be in terms of v, you will use that in the revenue to the auctioneer. The probability reasoning, the probability part, where I have discussed is V1 greater than V2 or V2 that greater than V1, that logic or that rationale is going to remain the same. Only this value which we eventually plugged in over here, half max V1, V2, only that thing is going to change if the strategy is something else. Okay, so let's take a small break here, and I will leave you with the next question.
Madam.
Yeah.
While you said that the strategy can be quadratic or anything else, so this means that in the questions when it was given like that the bid strategy is vi cube or vi square, is it what you mean by saying that the strategy can be quadratic?
Yes. So in the assignment or even in otherwise, even in the books, like sometimes you are given some other function for the other player's bidding strategy. So if that is the case, then I can't solve it in the class today because you still have your assignment to go. And yeah, so you can try solving it yourself this time. If you have trouble, we will discuss it in the next class. But that is what I meant. Like, yeah, the strategy. So the simpler case is when it is quadratic, or why isn't the slide changing? Okay, the slide is getting stuck somehow. It's not showing the question. A minute. Yeah. Okay. So, yeah, I was saying that the strategy of the other player can be any function. Okay, there's no limit on which function you can use. The simpler cases are linear, quadratic, or some other form, some other combination of the two. So those are the only ones which are there at your syllabus level anyway. So instead of a v j plus c, it could be something kv square or v square or something like that. So you just do the similar reasoning, similar calculation. You just use the function whatever is given to you. Okay, so I'll take a short break here for 5 minutes or something, and I'll be back. And when I'm back, I will discuss the second price sealed bid auction and how we go about proving this. It's not a very difficult proof. Actually, I will ask you to try this out. This is very simple proof, but we'll discuss it anyway. Okay, so let's resume. So there are two more questions I have for today. Um, One is the second prize sealed bid auction, and the other is the first prize sealed bid auction for the N player uh, game. So I was wondering if it's better if I do the first prize sealed bid auction first, since we are already discussing that anyway, and then we can go to the second prize. But before I go ahead, if there are any other questions, you can let me know so I can discuss that also. Otherwise, I will just go ahead with this.
Yes, ma'am, one just small question. Uh,
Yeah.
in our last problem, we have taken two cases. The V1 is greater than V2 and V1 is smaller than V2. Why don't we
Yes.
take the option V1 equals to V2?
Yes, that's a good question. I think somebody was asking something similar in the um, discussion forum also. So let's look at this diagram here. You can see my diagram, right? So in a continuous random variable, the unique property it has is that it only has a probability density function. Okay, there is a probability density function fx. Let me say probability, let me write it here. Probability that x belongs to x is equal to fx into x, right? Now, if you want this x to be even infinitesimally small, it is still fx into dx, right? That is how the probability is defined in this case. Now, imagine if this dx is 0, then what happens? It becomes 0, right? The
Right.
probability that the random variable is lying in a particular interval, small x, is probability density into that interval x, right? And in our unique case, if x becomes equal to 1, which I have not written, I have just taken the general function formula, it is fx into x. Now, if x is the interval here, let me mark this also. This is x. So if this red colored small x is x, then the probability that the random variable belongs to into that fits into that small interval x is fx into x. But if that interval x itself is 0, it is a point, right? A point has no length.
Okay.
Then the probability becomes 0, right? So the probability at any particular point is 0. So that is why we are only using, if you see everywhere, we have not said anywhere that vi is equal to this or vj is equal to this. We have only used lesser than, greater than everywhere. And that is why when you say, well, lesser than or equal to, it is the same thing as saying less than,
Okay.
because equality is always 0. So similarly, when you ask about the case where vi is equal to vj, that probability that vi is equal to exactly something itself is 0. So the probability that vi and vj are equal to each other is anyways going to be 0.
Right.
So in some textbooks, you may find that they define that case separately, that if vi equal to vj, this is how the allotment happens or something like that. But you generally don't need to do that if you're taking a continuous random variable. And this is not going to be the case in a discrete random variable, because in a discrete random variable, you're not taking a density function, right? You generally take a probability mass function, PMF, not a PDF. And PMF is different from a PDF. It's not defined in this way. PMF is the probability of X equal to X, right? So in that case, it is very much valid and equality carries its own meaning. But in the continuous case, it doesn't carry any meaning. Okay, so I thought I will discuss the N player game also in the same sequence instead of later. So this class is anyways a revision. I'm not discussing anything particularly new here, but just to introduce you to the rationale of n-player games and how you can deal with it. So my screen is visible, right?
Right. दिख रहा है.
Okay, yeah, I think my own laptop screen visibility is low. Okay, that's fine. Okay, so in this case, we are saying that n-player game is similar to whatever we just discussed, where there are, say, n players, and we are saying that valuation of any player I, okay, is vi, and it follows the uniform continuous random variable, uniform continuous distribution over the interval 0, 1. You can say for all I. Okay, and now we need to just basically solve for the equilibrium, and we have to prove something, right? We'll see what we have to prove. Once we solve it, I think we will anyways come to the proof. So let's write the utility of player I. Okay, there are any number of players, not any, sorry, there are n number of players. Now I am the ith player, that means there are remaining players are n minus 1 in number. So if I'm writing the utility of any player I, this is without loss of generality because I'm writing for the most general case. We're still on the first price seal bid auction, so this is going to be VI minus okay, yeah, I made a mistake in my notes, but anyway, if BI is greater than VJ for all J not equal to I. Okay, now I've written this in just one line for all J not equal to I, but what we mean over here is J is equal to 1, 2, 3, blah, blah, blah. N minus 1. Okay. And if you want to make it even more clear, you can write I minus 1, I plus 1 instead of this 2, 3, blah, blah, blah. I minus 1, I plus 1, dot, 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 n minus 1. So I've, just to make it simpler and a little bit more concise, I've just written for all J not equal to I. What I mean is this, that J can take values 1, 2, 3, 4, I minus 1, I plus 1 up till n minus 1. Or actually this will be n because you've already skipped I, right? So here I is missing. Total is n minus 1. We write this also. Okay, and is equal to 0 otherwise if BI is less than BJ for all J not equal to I. This also means the same thing. So now we are again given the same thing, that the linear expression A plus C Vj, we are given that the other players using this strategy, we have to prove something. I will come to the expression later. I don't want to give it away in the beginning. Let's write the usual thing we do. The expected payoff of player I is, now the value of the payoff is Vi minus Bi if he wins into the probability of win plus payoff when he loses into probability of not win or loss. So this is what Vi minus Bi into the probability that win means how many ways can he win. For him to win, for player I to win, Bi must be greater than B1, must be greater than B2, must be greater than B3, blah, 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 must be greater than Bi minus 1, must be greater than Bi plus 1, must be greater than Bn, right? So there have to be n minus 1 conditions satisfied for this player I to win. So just to write it in a slightly succinct mathematical way, let me write the same thing which I wrote, bi greater than bj for all j not equal to I. I don't want to write the whole lengthy thing, but this expression captures the same value, whatever I just explained in words, right? Now let's go back to what we mean, what we did, the same thing we did last time. Now bi, oops, sorry, this is bi greater than bj implies that bi is greater than a plus cvj, implies that bj is less than bi minus a by c. Same thing we did last time, except that the only thing we are doing this time is that we are including the probability of that particular condition being satisfied for n minus 1 players, not just one player. In the 2-player case, we had only one player, but in the n-player case, we have n minus 1 players to consider. Probability Vj less than Bi minus A by C. Now, this is what? Sorry, I think I missed something important here. So yeah, this part is fine. Bi is greater than Bj for all j not equal to 1. Let me expand this a little bit. One step which I just explained, but which I didn't write. Let me move this down. Okay, so this, let me simplify this, is equal to probability Bi greater than Bj into n to the power n minus 1. Okay, because when we say for all j not equal to I, we are obviously talking about n minus 1 of these things. So this thing, this probability expression, because its probability value is the same for each of those n minus 1, we can just simply put this, replace this expression with probability Bi greater than Bj, any particular Bj to the power of n minus 1, because all players are identical. So if you take the probability that Bi is greater than Bj for any j, then if you just raise that to the power of n minus 1, that includes all the possibilities of all the rest of the players. Is that clear? I don't know if I've explained it properly. So this also becomes the same thing, because we are talking about identical players, right? So J here represents any one of the players, 1, 2, 3, 4, 5, whatever, as long as it is not I. So if this condition is satisfied for any J, this is an expression, it's not one number, right? It's an expression, it's a condition which we are defining for a particular thing to happen, for player I to win. So this condition needs to be satisfied for all players J. And this condition is the same for all the rest of the players. That is why it becomes probability of all of these conditions getting satisfied at the same time. Hence, probability Bi greater than Bj to the power n minus 1. So then we know that probability Bi greater than Bj is this value, Bj less than Bi minus A divided by C. So I just replace that expression in the bracket over here. The rest of it is the same. So that is the main, the main thing we had to do. Now, if we use our previous reasoning of the CDF, then let me actually make this more clear. It is this. It is not, I think in some of the books, this is not written correctly, but the correct expression is this. The probability of Vi less than Bi minus A by C, the whole thing to the power n minus 1. So here also when I'm writing this, let me make this clearer. This whole thing is to the power of n minus 1. Okay. So here we can simplify this now. Now this expression is nothing but the CDF. Therefore, the value of the CDF fx of probability capital X less than or equal to small x is equal to x, right? So this becomes bi minus a by c to the power n minus 1. This is the only difference. This is all that is different between the previous problem and this problem. So now we know the expression for the expected revenue of player I. Now player I will maximize this. Therefore, we'll take the maximization condition. Now, this is two functions, product of two functions. We just take the differential of first, leave the second alone. Then we take the first as it is, and we take the differential of this one, 1 by c. This is going to be, say, 1 by c bi minus a n by 2, right? And n minus 1, yes. This n minus 1 will come down. This becomes n minus 1 divided by c to the whole, and this expression to the power n minus 2. So this is a very ugly expression. We just need to equate it to 0, thankfully. So there is some unpleasant algebra we need to do, but there is no getting away from it. So yeah, sorry, I missed the c there. So this is bi minus a by c to the power of n minus 2. And we take this expression here, plus n minus 1 by c into minus br. This is equal to 0. So now this bracket expression is what we need to simplify, actually. So let's do that. 1 by c, we can take it outside, actually, if we want. It's not going to matter too much. A minus bi plus n minus 1 into vi plus n minus 1 into bi is equal to 0. That's what I'm getting. I hope it is correct. Yeah. So let's simplify this. N minus 1 becomes n minus 2 vi. Okay, am I making some mistake? Yeah, there's a minus here. That's why I thought there's something wrong. Yes. Okay, so this becomes minus nbi. This minus 1 plus 1 gets cancelled out. Plus a plus n minus 1. We just take the okay, so now we have derived some expression, all right, for bi, and we need to check once again, as before, if this is conforming to this linear strategy which we were given. Where is that thing? It was given somewhere. Yeah, we are given this bj is equal to a plus cvj, and this is the same thing we want to check if we are getting A plus C Vj. So we are getting this in the, it's of the form, oops. So if we equate A is equal to A by N is equal to 0, then the first term disappears as before. And if we plug in C as equal to N minus 1 by N, then we get the same expression. So what we get is that Bi is equal to 1 minus 1 by N Vi as the best response of player I. And this is what we had to prove. I didn't want to bring out the expression first before because I wanted to make sure we arrive at it organically on our own without messing around too much. So this is the proof which was required, and we have kind of proved it. So it's just the only difference between this problem and the previous problem was that we took the probability to the power of n minus 1, and here we did some ugly algebra and we got this expression. We didn't do anything too different, but it's just important to remember the logic we have used.
Okay, ma'am, just a few steps back.
Yeah,
there was a product of two expressions equated to 0.
1 minute, let me just move this thing. It's looking very weird actually. The zoom level is very bad. So. Yes. Which one are you saying? Somewhere here?
Steps back, there was a product of two expressions equated to 0. Bi minus by C whole to the power n minus 2 and then multiplied by 1 by C.
Yes, this one. The screen is dating.
Yes.
Yeah.
So one interpretation could be that the first expression equals to 0. That's why the product is 0.
Yes, that is one of the expression. Yeah, you mean this one, right? Where we have Bi minus A by C to the power n minus 2. That can be that can be one equilibrium, but that is not the one which we are looking for in this particular question. So that's why I ignored it. You're right. Or you can say or Bi is equal to A. We don't know the value of A, but it is equal to some constant A, because A is a constant. So in which case we are saying that I'm going to bid the same amount irrespective of what the other guy is doing, irrespective of what my own valuation is. That is the only other equilibrium, which is not it is a possible, it's a possibility if A is some constant and C is equal to 0 instead of A, then you get this response, Bi is equal to A. And that is also a feasible response, and that means that in this expression Bj equal to A plus C Vj, C is equal to 0, and hence we are back to the same thing, that both the people, I player I and J, any player J for example, not both actually, all the n players are going to bid the same value, constant A, irrespective of everybody's valuation. So it's possible that can be a Nash equilibrium. I don't know. I haven't I haven't reasoned it out. But in this question, we were actually asked to prove that this is one of the Nash equilibria, 1 minus 1 by n into Vi. So that's why I ignored that part over here. So this logic is a little bit different from your usual mathematical logic actually, where you are supposed to get one answer in the end, right? And you solve the question and you get some nice value in the end, and that is your answer. But in game theory, that doesn't happen many times, especially when you really start doing a lot of continuous functions and all that. Then you don't get like one answer for a Nash equilibrium many times. You will get a expression, or you will get some condition, or you will get multiple Nash equilibria. So even in like some of the continuous cases, there can be like situations where there can be only one Nash equilibrium, but most of the times that is not so. You get like a huge pool of things which can be a Nash equilibrium. Okay, so anything else? Okay, so I'm taking that as a no. So let's go to the second price seal bid auction. We are given that a house is to be sold in a second price seal bid auction and there are n bidders. The valuation of each bidder follows a probability distribution with the CDF of capital Fi for the ith bidder, which is the same thing as saying that it has some distribution. Now, we are not given the distribution. That's what it means, that you're just given that F is the CDF, but we don't know what is the form of that CDF. What you have to prove is that there is a symmetric Nash equilibrium in which bidding one's own valuation is a weakly dominant strategy in the auction. And this result is it's independent of the probability distribution of the valuation of other bidders. Okay, so this looks like a slightly tricky question because you're not given the functional form of the probability distribution of the player's valuation, and you are asked to just prove that you're bidding your own valuation is the weakly dominant strategy. So now the good thing about this question is that you're not asked to find the Nash equilibrium or to prove any Nash equilibrium or anything of that sort. All you're asked is to check or to prove that a certain given strategy is weakly dominant. And why weakly dominant? Why not strictly dominant? We'll look at that, but also because we know that in any case, in the case of continuous random variables, the equality itself doesn't actually carry too much meaning anyway. So we don't have to like worry too much about it in the long run. Let me just make this a little bit tidier so that it can make sense. Otherwise, when I zoom in and out, the whole thing is not going to. So actually, this question, it doesn't even require too much of mathematical calculation or explanation. Okay, I think it's looking okay now. I'll fix the rest after the class, but let's move on. Okay, so you're given there are n players with valuation VI following a CDF of say Fi. That's all. Okay, for all I. Each pair has the same distribution. That much you are given. They are not all different valuations. I mean, they're not all different distributions. The form is the same. So, for example, they all are uniform, or they are all normal, or they are all something else. We don't know what exactly, but we know that they all follow the same functional form. So just so some places it may say that it's a Vickery auction. Vickery auction is also a second price bid auction only. So we are saying that bidders are simultaneously bidding. This part is important, that they are bidding simultaneously. B1, B2, blah, 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 Bn. Okay. Highest bidder is going to win and he's going to pay the next highest bid. So let's write down the utility function for player I. So I'm writing this in terms of I and J just to capture the sort of like the more general scenario, but you can also write it as, if you want to write it in a more complex way, you can just write it as ui bi comma b minus I, or you can write this as u b. This is also the correct mathematical expression. When we write b minus I, that denotes that it is the bidding strategy of all the other players other than other than I. Okay, now let me just explain the it is 0 if p is less than bj, right? And we are not considering the equality, so I'm leaving that out anyway. Now this is like a, other than the fact that we have used I and j, this is a pretty standard expression. Instead of ij, you can use 1 and 2. If it is a two-player case, all we know is that this is true for all j not equal to I. This is the same thing. Now, we know that all of the players j can be any player other than I. Any player j has the same CDF fj. It follows the CDF fj because vj follows the CDF fj. So because vj is following fj and we know that bj is okay, is this given? I think, okay, if it's missing in the question, you can assume that bj is a linear function of vj. So, you know, bj is also following the same distribution, fj. Now, let's just pause to think a little bit here. We don't have to do anything more than this actually in this question. If you want, you can draw the diagram, but you don't necessarily have to draw the diagram. So there can be like maybe 3 cases here. The first case is where not B, VI is greater than BI is greater than BJ. So in this case, what happens? Player I wins, right? His payoff or his utility, you can write, is VI minus BJ, which is greater than 0, because VI is greater than BI is greater than BJ, right? So in this case, he's actually getting a positive payoff, and in this case bi is less than vi, right? We have just considered the possibility what happens if that is the case. So let's leave this as is for the moment. If we need to, we will come back to it. Then there is a second case where bi is greater than vi is greater than bj. Now, this is an important one where the player I is bidding more than his valuation, his or her valuation, but is still winning and is paying eventually BJ, right? Again, player I wins and UI is still VI minus BJ and it is still positive, right? Now see, over here, if the player I bids something more than VI, is it making any difference? It's not going to make any difference because he's still going to get the same payoff. So if BI is equal to VI, UI is still equal to VI minus BJ, which is greater than 0. So that means that bidding his own valuation is doing exactly as well as bidding something higher than his valuation, right? That much is clear to us mathematically. We don't need to do very rigorous maths for it. And then there is the third case where BI is greater than BJ, but this is greater than VI. Right? Now, in this case, the bidder is winning, of course, but what is happening? After winning, he has to pay BJ. So, player I still wins. But his payoff is now, sorry, somebody wants to answer.
Valuation will be negative.
Yes,
Payoff.
exactly. His payoff is going to be negative. So now the expression for not pi, sorry, we were using u, right? So ui is now vi minus bj, and it is less than 0, right? So one thing we can see that if his valuation is less than bj, then bidding any value bi greater than vi and hence greater than bj is weakly dominated strategy. You never want to do that. Right? If your own valuation is less than the bid of the other player, the second highest player, or any other player who could be the second highest bidder, if your own valuation itself is less than that, you will never want to bid more than your valuation, because if that is the case, if that ends up being more than BJ, then you're going to have to pay BJ and you will end up with negative valuation, right? So this case is not desirable for player I at all. So let's say this is not actually weakly, this is a strictly dominated strategy. And there can be one more case, but it doesn't sort of make a huge difference, where BI is greater than, no wait a minute, not this. It was just there in my head, I forgot. VI is greater than BI we have considered. Yes, VI. Yeah, this is a redundant case actually, because in this case, player I loses. Therefore, UI is 0 because this is a second price sealed bid auction, right? So in this case, if your valuation is higher than BJ and your bid is lesser than BJ and is lesser than your valuation, you're losing. So your payoff is anyways 0. So now let's look at the strategies where his payoff is not 0. Now we have considered 4 cases, and I think these 4 cases capture the complexity of the entire problem. These are the 4 cases which can possibly arise. In the last one, his payoff is 0 because he's losing. So of course, in that strategy, we don't need to consider for the moment. In the third case, we know that if he's bidding a value higher than his valuation, and if that bid is higher than the other bid and he's winning, then he's going into a negative payoff. So of course this is a weakly or at least a strictly dominated strategy. So this he's never going to want to play. Now let's look at the first two. In both of the first two, what we are doing is that my valuation in the first case, first scenario, my valuation is higher than BI and it is higher than BJ. BI is greater than BJ. So in that case, player I wins and he makes positive profit. So now if VI is greater than BI, it doesn't actually matter whether I'm bid higher than, if as long as I'm bidding something more than BJ and I'm winning, I don't actually, I don't actually make any other difference, doesn't make any difference to my equation because my valuation is the same number. Valuation is not changing. Valuation is VI and I'm paying BJ. So if BI is anything between VI and BJ, I'm still winning, right? So if in the first and second case, basically what you see is that there is no huge difference. Even if by bidding higher than VI, which is the second case, you get the same payoff, right? This expression, let me highlight it. UI is equal to VI minus BJ is greater than 0. And here also you have UI is equal to VI minus BJ greater than 0. This expression and its value is going to be the same, right? So bidding higher than your valuation is not necessarily giving you any better payoff. Bidding less than your valuation is also giving you the same payoff as long as BI is greater than BJ, which means that if you actually bid equal to your valuation, you have the highest chance of winning the bid without running into losses. right? Because if you bid higher than VI and you end up winning and your VI is actually less than BJ, then you lose, right? Whereas which is what happens in the third scenario. But in the first two scenarios, you can see that bidding equal to VI or bidding greater than VI is giving you the same payoff. So this is actually all there is to this particular situation, because in this we have not assumed any functional form of BJ or VJ, because in this particular thing we are not actually concerned with VJ, we are only concerned with BJ, and we know BJ follows a certain distribution, it could be any distribution, but the rationale of second price sealed bid auction remains the same irrespective of what the functional form might be, right? So in this case, I mean, am I clear? Is this logic making sense? If you want, you can also draw a diagram. Just quickly draw the diagram. So let's draw the diagram of UI. I can make it U1 also. Either way it is okay. I'm just showing the same thing on the diagram here. This is, say, suppose V1. Oh, sorry. Yeah, VI actually. Why did I erase it? VI, and here you have BJ. Then in this case, if you're increasing VI in this direction, so BJ is greater than VI. Look at the x-axis. On x-axis we are measuring VI, and on y-axis we are measuring UI. So if your BI is less than BJ, then in this whole region you're actually losing. Let me use some other color. So in this whole region BI is less than BJ, so you're losing, right? So your payoff is what? 0, which is what I've shown with the thick line. Now, if BI is greater than BJ, then your payoff becomes some, some value. Now, what is that value? Your payoff is VI minus BJ, right? But VI is less than BJ. So in this entire region, your payoff is actually negative, which I'm showing with this line. Is this making sense? Similarly, if you want, you can make the other diagram. It's just going to be the opposite. In this case, I'm inverting the relationship between VJ and VI. Now, in this case, VI is greater than BJ. So, well, here, let's see. If BI is less than BJ, you're losing over here. Yeah. So far, you are losing, right? Now, if BI is greater than BJ, you are winning. And your payoff is what? VI minus BJ. So now, irrespective of how high you bid, your payoff is still the same. This value is VI minus BJ. And this is your value. So this diagram just helps you visualize what is happening. You don't actually need the diagram, but if it helps, you can refer to it. All I'm saying is that if, in this case, you can look at first two scenarios. Bidding higher than his valuation is not going to give him better payoff than bidding equal to his valuation. Because bidding higher than his valuation, when your valuation is already greater than BJ, doesn't make any difference. I mean, you're still getting the same payoff, VI minus BJ. Whereas bidding more than your valuation, when your valuation is less than BJ, actually gives you a negative payoff, right? So in the first case, you're doing as well as bidding equal to your valuation, and in the second case, you're doing worse than bidding equal to your valuation. And hence, you can say, I'm not writing it down because that takes too much time. If you're asked this in a question in an exam, like in a subjective thing, then you can write down this, whatever I'm explaining in words, you need to write that down. and you can explain that rationale, that that is the reason why it is a weakly dominant strategy. Why weakly? Because you're doing just as well as other scenarios where you're getting vi minus bj. Okay, so I think we can wrap it up with this. This is the reading list for this particular week. So just so you know, in case you're not paid attention, I actually give a reference reading for every week, because not all topics are covered with the same level of rigor or same level of simplicity in all the books. Okay, the screen is not updating, I'm afraid. Yeah. So this is the reading list for this particular week. For statistics, probability and statistics, the fourth book is the one I prefer. I use this book. And it's not too lengthy, but it explains things in a very intuitive way if you want to refer to it. The primer in game theory has some explanation on Bayesian auctions, and so do the other two. So only these three books have a decent explanation of Bayesian auctions, as per me, at least. But of course, if you prefer some other book, that's your choice. And I have given most of the references in the diagram, sorry, in the slides. But most of these are actually very standard questions, so you'll find them in almost all the books. It's nothing particularly great about it. Okay, so I think that completes today's class, unless there are any other questions. Okay, so I'm assuming there are no other questions. So thank you for joining. I'll upload the annotations, I mean the notebook and the slides by the end of the day.
Thank you.
Okay, thank you. Thank you. See you next time.